What's up, guys? In this video, I want to go over the top topics that you need to know that you can expect to come up on your semester one pre-calculus midterm. So I'm going to go through each of these topics. I'll kind of give you a broad little overview because I'm not going to hit every single topic, but ones that you can kind of further investigate, make sure you understand. But then also I'll dive a little bit deeper. I'll go through a basic example as well as a little bit more difficult one that you might expect to be on your midterm. So if you have a midterm coming up or you just want a little bit of a refresher from semester one, then this video is exactly for you. So let's go and get into the topics that I want to focus on in semester one. So the first one is just going to be functions as well as transformations. So we want to look at, make sure you know the domain and the range, even and odd, make sure you can how to identify them algebraically as well as graphically, and as well as be able to describe the transformations of a function. So that's the problem that I'm going to start off with this one is describe the transformations to get the graph g of x from f of x. So let's go and take a look at what we want our f of x to be. And let's just kind of work through something basic. Let's say f of x is going to be an x squared. We should all be familiar with the quadratic function. And then let's go ahead and make g of x here a negative. Let's do an x minus 3 quantity squared plus 1. All right, so what we basically want to be able to do is say, how am I going to get g of x from f of x? So if this is going to be my original graph, what exactly am I doing? And basically what I need to do is understand what are the transformations that are being applied to g of x. So you can see there's a couple things that's going on. We're multiplying by a negative on the outside. We are subtracting a 3 on the inside of the function, and we're adding a 1 on the outside. So the main thing I want to stress to you about remembering transformations with functions is it doesn't matter what the function is, guys. It doesn't matter if it's a quadratic, if it's a radical, it's a reciprocal function, square root, logarithmic, sine. Whenever you have operations that are outside the function, okay, those are going to be what we call vertical transformations. It's either shifting it up or down, stretching or compressing up or down, or reflecting up or down. So let's go and take a look at our two outside operations. We have a multiplying by -1 and we have an adding a 1. So whenever we are multiplying by a negative on the outside, that is going to be what we call a reflect the x-axis. Now, if that number was larger than 1, then we'd have a vertical stretch. And if it was less than 1, it'd be a vertical compression. When we are adding or subtracting outside of the function, that's going to be shifting the graph up or down. Since we're adding a 1, that's going to be actually a shift up 1 unit. Now let's go and take a look at the transformations inside. These are going to be your horizontal transformations. If you had a negative multiplied by your x on the inside, that would be a reflection about the y-axis. If you had a larger number or a number multiplied by that x, which is larger 1, that'd be a horizontal compression. If it was less than 1, but between 0 and 1, that'd be a horizontal stretch. And in this case, when we are subtracting, that's actually going to be a shift 3 units to the right. So we'll say is shift 3 units, can't write there, 3 units right. Okay, and again, that just comes back from this basic transformation function here, guys. The a times b, x minus c plus d. So you can see it's always the opposite. So it's the plus d is the exact same sign, whatever it is. But this inside, this is going to be opposite. So if it's plus, you go to the right. I'm sorry, if it's plus, you go to the left. If it's negative or subtract, you're going to go to the right. All right, let's go and take a look at domain for functions. Guys, this is a common recurring theme. You need to make sure you understand how to be able to identify the domain of a function. So in this case, I have a h of x is equal to the square root of x minus 4 divided by x squared minus 25. Now, the two things that I really drill with my students to make sure they understand when we're trying to identify the functions, and again, this is specified for precalculus. You can't divide by 0. You can't take the square root of a negative number. So we have two things going on here. We have an expression in the denominator, and we have an expression under a square root, right? So we know we cannot take the square root of numbers that are less than 0. So what I'm simply going to do is I'm going to take my quantity, my quantity that is inside under my radical, and I'm going to set that to less than or equal to 0, because I need to be able to identify all the values that are going to be Wait, no, that needs to be greater than or equal to 0. Jeez, Mr. McLogan, come on. These values need to be greater than or equal to 0. Okay, so greater than or equal to 0. And then I can simply just solve this plus 4. X has to be greater than or equal to 4. So that means the domain is now restricted here for all values that are 4 or larger, because it can be 0. You can take the square root of 0. You just cannot take the square root of negative numbers in our real number system. Now, the next one is I got to identify, well, what are the values that are going to make my denominator equal to 0? So all we simply do is take our quantity that's in our denominator, say x squared minus 25, and we're going to set that equal to 0, because I want to find the values that make my denominator 0, because those values are not going to be included in my domain. So I'll add a 25 to both sides. I get x squared equals 25. And do not forget, this is probably going to be the most common thing that students will make mistakes on, is forgetting to introduce the plus or minus. So x is going to equal plus or minus a 5, right? So when you introduce the square root, make sure you introduce the plus or the minus. So what right now I have, x cannot equal a plus or minus 5. Okay, so those are the values that make my denominator 0 that are not going to be defined in our domain. Now, sometimes you can identify the answer rather quickly, right? Just from there. But sometimes you just kind of need a little bit of visualization of understanding what is our domain going to look like. So a lot of times I tell my students, just draw a number line. All right, so if here's going to be 0, let's say here's negative 5. That is an undefined value. And let's put a 5 here. That is an undefined value. But then it says my domain is going to be only for values that are large or that are equal to 4 or larger. So let's put 4 right here. And then we're going to do an included circle. It's going to go to 5, but we're going to have to skip 5. And then it's going to go all values over there. Okay. So if I want to write my domain in this case for this problem, I'm going to say the domain is going to be including 4. So we're going to go from 4 to 5. But then I'm going to skip over 5. That's why I use the parenthesis, because it's not included. Union 5 to infinity, because this continues to go in there. So there's none of these values over here are going to be included in your domain. Next one, given f of x and g of x, find the composite f of g of x and its domain. So composition of functions, very, very common. Make sure you are understood how to do all the operations, adding, subtracting, multiplying, dividing, but composing a function with another function is critically important. Now, a lot of times it won't be written like this, but I was kind of limited on how I had to text it. So a lot of times you'll see this as written as the fog function, okay? Just remember, f of g of x is the same thing as f of g of x. Now, again, if this notation gets you confused, go back to something simple, right? If I had like f of x equals, I don't know, x plus 1. And if I say, what is f of 0, what do? You replace the x with the 0. So this is going to be 0 plus 1. Okay, so all we're doing in this case is we're saying, what is f of g of x? So in this example, what I would simply do is just plug g of x in for my 0, right? So I'd say a g of x plus 1. Now this example, this does not make any sense because I have not defined what g of x is. So let's go through an actual problem. What if I had, actually, let's just go ahead and erase that, because for those of you that are on the video, it'll make some sense. But for those of you that are looking at the cheat sheet, which I'll have this print down, so you guys can go ahead and print this down below. I'll get it to you, for free. And then also, if there's any other stuff that you guys want for pre-calculus, as far as, getting prepared for your midterm, I'll make sure I have those provided to you guys in the description down below. So let's say f of x is equal to 1 over x plus 2. And let's say g of x is going to be 4 over x minus 1. All right, so given f and g of x, find the composite of f of g of x. Okay, so we're going to plug g of x into our f of x. Okay, so we're going to say f of g of x that's going to look something like this. 1 over a g of x plus 2. Just like we did in that previous example. However, ladies and gentlemen, what do we know? We know what the value of g of x is, right? We now can rewrite this as 1 over a 4 over x minus 1 plus 2. Now, before we go ahead and get to that, or before we get to the domain, let's see, can we simplify this? Well, what we could do is we could combine our denominators here. We can rewrite that as 2 over 1. Then we can get a common denominator by multiplying by x minus 1 over x minus 1. And then I'm just going to kind of continue, because I'm a little limited on my space, with my equal sign. So I have a 1 over a 4 plus a 2x, you can apply distributive property, minus 2, all over our common denominator, because now they have a common denominator of x minus 1. And I'm left with a 1 over, let's see, that's going to be a 2x plus 2 divided by a x minus 1. Now, again, you have like this fraction being divided, or a number being divided by a fraction. So what we can simply do is multiply by the reciprocal. And what that's going to do is that's going to get rid of this fraction in the denominator. And that's going to leave me with a 2x plus 2 in the top, which is going to give me a final answer of x minus 1 divided by a 2x plus 2. Okay, so that is going to be our final answer. That's going to be the composition. Now let's go and check out what our domain is going to be. So there's two ways we want to check out the domain of our composite function. We want to take the domain of our resultant composition, so our resultant function, as well as what is the inner function that we plugged in. So if we look at the domain here, we know domain is going to be all real numbers except x cannot equal a positive 1. And then if we look over here, we're going to have a 2x plus 2 is equal to 0. You're going to have x cannot equal a negative 1. So my domain is going to be all real numbers except for a 1 and a negative 1. And again, if you have trouble visualizing this or writing the domain down, now again, you could be working with multiple choice, and that'd be great because then it's a little bit easier sometimes to identify what the domain is. But if you don't, then just look at a number line. My domain is going to be all real numbers except for negative 1 and 1. So it's going to go that way, it's going to go between these two, and it's going to continue going that way. So if I want to go ahead and write my domain is going to be from negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. There you go. All right, the next topic that I want to cover with you guys is going to be rational functions and asymptotes. So I want to focus on identifying the vertical, horizontal asymptotes, the vertical asymptotes, the horizontal asymptotes, the slant or the oblique asymptotes, making sure you're comfortable simplifying, solving, as well as graphing, and then also making sure you're going to be able to identify some holes. But let's just go through a quick little review with vertical asymptotes and horizontal asymptotes. And then also I'll throw in a little topic about holes as well, because I think that's important. So it says find the vertical and horizontal asymptotes. So let's go over a function f of x equals a x minus 1 all over a x squared minus 9. Okay, so the main important thing, guys, when we're looking at vertical asymptotes is those are going to be the values that are what we call a non-removable discontinuity. Those are going to be values that make our denominator 0 that cannot be simplified or factored out. So we always want to look to factor. How can we simplify this? Now, thankfully, over here, there's nothing in our numerator we can do, but in our denominator, I can simplify this to an x minus 3 times an x plus 3. Okay, that's going to be your difference of two squares. And then if you want to identify the values that are going to create your vertical asymptotes, just set your denominator in factored form equal to 0. So I have an x minus 3. Now, again, this is a zero product property, but I'll just work it out here to have that. So therefore, I can say x minus 3 equals 0 and x plus 3 equals 0. So therefore, x equals 3 and x equals a negative 3. Again, those are going to be my vertical asymptotes. Now, for the horizontal asymptotes, we want to apply what we call the horizontal asymptote test, all right? And I'm not going to write out the whole thing. I'm just going to summarize it. So there's three options we have. We could have the degree of our numerator be less than the degree in the denominator, which we have in this case. When that is possible, or when that occurs, our horizontal asymptote is going to be y is equal to 0. When we have the degrees are exactly the same, so let's say this was x squared and let's say this was x squared, then what we'd have is you're going to take the leading coefficient of your numerator over the leading coefficient of your denominator. So y equals leading coefficient over leading coefficient. And a lot of times that's going to be a fraction, or it just reduces down to an integer. And then the last case is when the degree in the numerator is larger than the degree in the denominator, you're not going to have a horizontal slant, or you're not going to have a horizontal asymptote. You may have a slant asymptote. So that's what we need to go ahead and check. Now, the last thing I just want to bring up is what about Ms. McLogan if we had a hole? How does like the holes play into vertical asymptotes and horizontal asymptotes? So I wasn't really planning on doing that, but let's just do a quick little example. Let's call this g of x. And let's say this was x minus 1, and this was a x squared minus 1. Okay, now again, don't just be dividing things out here, right? We got a factor here. And so when I go ahead and factor this, I get a x minus 1 all over a x minus 1 times a x plus 1. Okay, so what I want you to see is since these are separated by multiplication, those expressions are going to go and divide out. So my simplified version of my g of x is going to be 1 over a x plus 1. So therefore, I have a vertical asymptote at x equals negative 1. Now I might say, well, Mr. McLogan, it's x plus 1. Yeah, but when I set x plus 1 equal to 0, right? When you say x plus 1 equals 0, you get x equals a negative 1. That is the value of my vertical asymptote. However, x minus 1 is still this, or when x equals a 1 is still a discontinuity. That still makes your denominator 0 because 1 squared minus 1 is still 0. However, it gets simplified out. So that is what we call a removable discontinuity, which again is going to be a whole. So I'll say as I have a whole at x equals a positive 1. So that's the difference between vertical asymptotes and wholes. Wholes can be divided out. Vertical asymptotes cannot. However, they are still undefined values for your domain. So make sure you remember that. All right, so I did mention about slant asymptotes. So let's go through an example of slant asymptotes. So again, this is going to occur when your degree in your numerator is going to be larger than the degree in your denominator. So if I had a problem like this, you can see here that the degree in my numerator is larger than the degree in my denominator. Okay. Now, again, you could have a whole, right? So you always want to look to factoring it first to see if things could simplify. I cannot factor this across real numbers though, and this looks a little difficult to go ahead and factor as well. So I would probably just hedge on my bet that, hey, there's probably a slant asymptote going on here. So to identify the slant asymptote, all we simply need to do, ladies and gentlemen, is apply long division. The quotient of that is going to give us our equation for our slant asymptote. And we don't have to remember about the remainder. Now, I know a lot of students hate long division, so that's why I think it's important for us to go through this step by step, okay? Now, you can see that we don't have an x in this case. Now, you can, if you are kind of familiar with synthetic division, you can create a space value if that makes you feel more comfortable. You don't have to, and it really kind of comes into, how comfortable you are with identifying the applying long division, and you can kind of leave this 0x out. But I always like to make sure when I'm setting up long division, you got to make sure you have things in standard form. Highest degree first, going down in descending order. All right, so let's go through the process step by step, okay? Because finding slant asymptotes is a very common topic for this midterm. So I'm going to say, how many times is x squared divided into x cubed? Now, ladies and gentlemen, if this gets confusing or you just want to double check your work, write it over to the side. How many times does x squared divide into x cubed? Right? It's just a rules of exponents problem. Remember when you divide exponents, you subtract the powers. X cubed, 3 minus 2 is 1. So therefore, that's going to be an x to the first. Now what we do is when we get our first term of our x to the first. When we get our first term of our quotient, we need to multiply that by both terms of our divisor. So x to the first times x squared is going to be an x cubed. If you did it correctly, you're going to get the exact same values here. And then x to the first times 1 is going to be a positive x. Here's where including this is sometimes helpful, okay? So you can line them up there because if you didn't include that space value, sometimes you don't know where to put it and you can get confusing. So I'm going to put brackets around here and I'm now going to subtract the rows, okay? So go ahead and subtract the rows. Now when I go ahead and subtract the rows, x cubed minus x cubed is just going to be a 0x cubed, so we can just leave that off. And then again here, you could put a space value here if you want. Negative 2x squared minus 0x squared, doesn't really matter, or you could just bring it down. That's going to be a negative 2x squared. And then 0 minus a 1x is going to be a negative x plus 1. You can just bring it down or subtract it from 0. It's kind of the same idea. All right, how many times is x squared divided into a negative 2x? Again, you're like, I'm not really sure. Okay, then write it on over here. How many times does x squared divide into a negative 2x squared? X squares divide out, right? So therefore, it's just left with a negative 2. Now again, negative 2 times x squared is a negative 2x squared. Negative 2 times 1 is going to be a negative 2. And then you could subtract your rows, but what's going to happen again, minus a 0x is just going to be, you're just simply just going to get a negative x. And then I forgot to do this. 1 minus a negative 2 is going to be a positive 3. But in this case, guys, it doesn't really matter because this is going to be your remainder. Because my x squared does not evenly divide into this negative x. So this is going to be a remainder. And the cool thing about with our remainder with slant asymptotes is they're converging to 0. So all we need to worry about is just going to be what is our quotient. So to find the slant oblique asymptote of this polynomial is simply just going to be x minus 2. So I can say the slant asymptote is going to be y equals ax minus a 2. All right, now let's get into polynomial functions and graphing. So find all the real zeros of the polynomial and state the multiplicity of each zero. So when we're dealing with polynomials and functions, we got to make sure we know multiplicity, zeros. And then also we want to make sure we can apply division, such as long division, as well as synthetic division, and know your operations like adding, subtracting, and multiplying. So in this first one, I think, being able to factor and find the zeros and identify the multiplicity is critically important. So let's take a function. Let's do p of x is equal to x to the 4th minus an x cubed plus a 6x squared. All right. So when we want to find the zeros, we want to find the values that are going to make this polynomial function equal to 0. Or we want to find the values that satisfy when this polynomial is equal to 0. Now, whenever you have a higher order polynomial, especially when it's a trinomial, I always think of factoring quadratics, right? But again, this is raised to the 4th power, not raised to the squared. So then I always want to look into what can I factor out? Is there any common factors I can factor out? And in this case, you can see I have the x squared that I can factor out. So simply what I'm going to do is I'm going to say p of x is equal to a x squared times a x squared minus x plus 6. And actually, we want to find the 0. So I'm going to set this already equal to 0. So therefore, we can go ahead and do that. Okay. Now, in this case, you could apply the 0 product property, but we also say, hey, I have a quadratic trinomial. Can I further factor that down? And what I'm looking at here is what two numbers multiply give me a positive 6. That means they both have to be positive or both have to be negative. But then are going to add, that's negative 6. That's wrong. I wrote that down wrong. That's supposed to be a negative because that would not work, right? Because you couldn't have a positive and a negative to add to there. So I wrote down this problem wrong. Oops. Apologies. That's supposed to be a negative. Because obviously, if you're thinking about factoring, ladies and gentlemen, and this is something I would do sometimes when I would change a problem on my students' midterm. Not going to lie. But at least what I would always make it up to them, I would give the problem for free. If they recognize the mistake that I made, I'd say, guys, number 17, the answer is B. And I always gave it to my students because that was my mistake. It shouldn't be your fault. All right. But I recognize, yes, my last number is negative. So that means one factor is positive, one factor is negative. They add to give me a negative 3. Immediately in my head, I am factoring this to a x squared times a x minus 3 times an x plus 2. Okay. Now again, this is a product of 3 factors equal to 0. So we can apply the 0 product property, set each factor equal to 0, and then we can solve, and that's going to be the zeros. So x minus 3 equals 0, and then x plus 2 is equal to 0. Now, there's nothing wrong with this written this way, but sometimes I like to write it like this for my students to see this factor. Because when we're looking at the multiplicity, what we're doing is we're looking at the power of the factors, okay? Now, multiplicity is very helpful, especially when graphing. That kind of explains this bouncing effect or this crossing effect. So if you have an odd multiplicity, that means the graph is going to cross at that 0. If you have an even multiplicity, that means the graph is going to bounce at that 0. So in this case, when you solve for this, you get x is equal to 0, but it has a multiplicity equal to 2. Over here, you have x is equal to 3, but the multiplicity is equal to 1. And over here, you have x equals negative 2, but the multiplicity is also equal to 1. So that's how you identify the zeros by factoring, as well as identify the multiplicity. Make sure you write them as factors, and you can identify what their power is, but they have to be linear factors. That means the x has to be raised to the first power as a linear factor, but then it can be raised to a higher power, and that will tell you the multiplicity. Find the polynomial of degree 4 with real coefficients that has the given zeros and multiplicity. Leave the answer in standard form. Okay, so let's find the polynomial, and let's say here is going to be my zeros. So I could say, so the zeros, let's do x equals 1 with a multiplicity equal to 2. And let's go ahead and do x equals a 3i. All right. Okay, so remember, it's really important to understand when you have a factor, I actually need to go back up here. These are what we call factors, right? But then when I added 3 over there, I gave me a 0. So all we're simply doing, guys, is we're working backwards, right? This is actually what we did. We took this factored form, we factored, or non-factored form, we factored it, set them equal to 0, and then we found the zeros. Now we're given the zeros. We want to find the factors. So if x plus 1 is a 0, that means x minus 1 is going to be a factor. And then we can set that factor equal to 0, right? We can set that as x minus 1 is equal to 0. And then if you add 1, you get x equals 1, right? So that's going to, x minus 1 is going to be a factor. But remember, it had a multiplicity of 2. Now, we're not setting equal to 0 because we're not solving it. What we're trying to do is we want to find the polynomial version of this. Or we want to find the polynomial that makes that with that factor. Come on. So it's x minus 1 squared. Now again, x minus 1 squared is not x squared minus 1 squared. It's x minus 1 times x minus 1. But hopefully you recognize that's a perfect square trinomial and you can factor that quickly to this. Okay, so there is our one factor. The next one is x equals 3i. Now again, as factors, that's going to give me an x minus 3i, right? If you subtract that over to get 0. But then remember, the complex conjugate always has to exist. So if you have x minus 3i, you have to have a x plus a 3i. Now we need to multiply this, but hopefully you recognize, again, this is a difference of 2 squares, right? So, and this is going to be -3 times negative, or -3 times +3 is a -9, but I times I is I squared, which is a -1. So therefore, this is going to give me an x squared plus 9. So now my p of x, which I'm going to call my polynomial, is going to be a x squared minus a 2x plus 1 times a x squared plus 9. Now, ladies and gentlemen, there's nothing wrong with applying distributive property here. However, on a test, or even not on a test, I would still probably prefer to use the box method, because what I have found when I multiply polynomials that are higher than binomials, by using the box method, I just eliminate so many mistakes on my end. So it's just something I prefer to do. Okay. You don't have to do it this way. It does take a little bit longer to do, but I have just found it is so much easier to visualize or to see where and if I make a mistake and to correct my answers. I don't know why I have it. Okay. So you take one polynomial on this side and you take one polynomial on that side. I don't like how that bar goes all the way across. It's kind of weird. All right. And then remember, multiplying, guys, you're just finding the area. So you're just going to do length times width for each box. So in this case, I'm going to have a x to the 4th. X squared times x squared is x to the 4th. X squared times -2x is a -2x cubed. X squared times 1 is an x squared. X squared times 9 is a 9x squared. 9 times -2 is a -18x. And 9 times 1 is going to be a +9. And the cool thing about this is, oh, actually, they're not on a diagonal. So let's go and write out now our p of x. So we have p of x is equal to, we have an x to the 4th. We have -2x cubed. 9x squared plus an x squared is going to be a positive 10x squared. And then we have a minus an 18x. And then we have minus a 9. Now I ran out of space, so I can just go ahead and shrink this down. And now everything is going to go ahead and fit. All right, let's go and work on our next one with polynomials, and that is going to be use the remainder theorem and synthetic division to evaluate an f of -3 for f of x. So let's go and take an f of x that's not going to be easy to evaluate for -3. So let's do a 2x to the 4th plus a 5x cubed plus a 4x squared plus a 7x plus a 10. Okay. So if I said evaluate for f of -3, okay, remember what that tells me, whatever this value is, that's going to be the remainder if I was to divide by the factor that gives me at -3. So again, let's say if -3 would be my potential 0, then I can say x equals -3, then x plus 3 is going to be my factor. So when I take my f of x and I divide it by x plus 3, that's going to give me whatever my remainder is going to be. Or when I take x plus 3 and divide into f of x, r is going to equal the remainder. I don't want to say equals r because that's kind of confusing. R would equal the remainder, okay? Or but whatever, but when I plug in f of -3 into that function, that's going to give me R, okay? Which would be represents the remainder if I were to apply division. But I don't want to plug that in there. That's going to be a lot of math. So what we can quickly do is we can use synthetic division to be able to figure out what the remainder would be, which would be the same as using the remainder theorem. Sometimes the remainder theorem is faster and easier, and sometimes using synthetic division is going to be faster and easier. So again, if x plus 3 is my factor, then this would be my potential 0, or the value that I'm going to use for my synthetic division. So I'll take that number on the outside, and then let's go and take all the coefficients of my, let's take all the coefficients of my polynomial. So let's write it like that. So again, make sure you have descending order and make sure you have everything listed. So 4, 3, 2, 1, 0. So I'll have a 2, 5, 4, horrible 4, 4, 7, and 10. All right, so bring down the 2. And then remember, first one is always a freebie. And then you multiply on the diagonal, add on the vertical. 2 times -3 is a -6. 5 plus -6 is -1. -1 times 3 is going to be a +3. 4 plus 3 is going to be 7. 7 times -3 is a -21. 7 plus -14 or -21 is going to be a -14. 3 times -14 is going to be a +42. 10 plus 42 is going to be a 52. That is going to be my remainder. So R, or f of -3, is equal to a 52. There we go. All right, the last topic that we usually cover on our semester midterm is usually going to be some trig, right? It's usually right around the end of the not school year, but the end of the calendar year. We get into some trig, maybe some unit circle, and then we send you off for 2 weeks and you get to relax, right? Unless you have that midterm that's after winter break, which I always hated. We used to have that in my school. And oh man, I felt so bad for the kids coming back from break and then had to take an exam. Like, it was tough. But this is the last topic we're going to cover on this one. So I have trigonometry. So find the period, amplitude, and phase shift for g of x. So let's give a g of x that's going to have all three of those. So let's do a -1/3. Let's do sine of x. So sine of 2x plus pi right there. And then, yeah, I don't really need that extra one. That's kind of weird. Okay, so -1/3 sine of 2x plus pi. Now, again, if you remember at the beginning of this video, I talked about transformations, right? It's the same thing, guys, happening over here. All right, now let's go and look at our transformation. So f of x equals a times times the sine of b times x minus c plus d. This is the exact same thing I gave to you at the beginning of this video, except I used like f of x or g of x in that case. But again, a and d are outside transformations. B and c are inside transformations. Now, when we're talking about amplitude, period, and phase shift, let's go over it. The amplitude is simply just going to be the absolute value of a. The period, and that's going to be how the amplitude, again, is the half distance from the max and the min of your vertical points on your graph. The period is going to be how long it takes the graph to repeat itself. So therefore, that's going to be 2 pi divided by b. And our phase shift is going to be how we're going to be shifting left or right, okay? So our phase shift is going to be left or right. We could have our starting point from on there. Because yeah, phase shift. Okay. Okay, and that's going to be your horizontal shift. So let's go and identify how to find the amplitude. Amplitude, absolute value of a. Well, my a in this case is a -1/3. So -1/3, and that equals a 1/3. For my period, 2 pi divided by b. B is what we're multiplying by x. Now again, notice this is not in that format, right? So what you should do is when you have a b and a c is make sure you factor it out. So when I factor out a 2, I'm going to be left with an x plus a pi halves, right? Because when you multiply that out, you're going to get that original answer. So my period is going to be a 2 pi divided by 2, which is just going to be a pi. And then my phase shift is how are we shifting left or right? Well, you can see since it's plus pi halves, we're going to be shifting pi halves to the left. And there we go, ladies and gentlemen. That's how you identify your period, amplitude, and phase shift. And this is going to be the exact same if you're dealing with sine as well as cosine. But you do start having some changes once you get into tangent because there's no amplitude and the period is pi compared to 2 pi. So make sure you review all those graphs as well. All right, last one, unit circle. Convert the angle from degrees to radians and then evaluate for tangent. So let's do one that's fairly basic here. Let's do 120 degrees. Okay, so how do you convert a degree to a radian? Now, I think it's really important that the more trig we do, the more familiar you are with radians. But sometimes converting is something we need to do. So all you're simply going to do is multiply it by pi over 180. Now I simply have 120 degrees times pi all over 180 degrees. Now I can just kind of simplify and say, what is the largest number I can divide in my top and my bottom? And I'm thinking 60. 60 goes in there 2 times. So it's 2 pi divided by 3. And again, your degrees are going to divide out. So therefore, that's a 2 pi over 3. Now, part 2 of the question says, can you evaluate for 2 pi over 3? All right. And evaluate is basically going to be, is look at the unit circle and the tangent of an angle on the unit circle is going to be the y coordinate over the x coordinate. Now, thankfully, 2 pi over 3 is on the unit circle. So, or the point, there's a point on the unit circle at 2 pi over 3. So I just need to figure out what those coordinates are. So let's do a quick little review of how to graph 2 pi over 3 on the unit circle. Remember, we're always going in standard form. So we're going to start on the positive x-axis and we're going to rotate counterclockwise. We know halfway around the circle, ladies and gentlemen, is going to be pi. So therefore, we could break that up into thirds and we're going to say 1/3, 2/3. So we're going to go to this point right over here. Now, hopefully, if you have the unit circle memorized, not the unit circle, the first quadrant of the unit circle memorized, you know that this first point is going to be 1/2, comma, square root of 3 over 2. And this point and this point are direct reflections of each other across the y-axis. So therefore, this coordinate point is just going to be a negative x coordinate, and the y coordinate is going to remain the same. So I have a negative 1/2 over a square root of 3 over 2. So now to evaluate the tangent, that's going to be my y over x. So all I'm simply going to do is take a square root of 3 over 2 divided by a negative 1/2. Now my 2's will divide out, and I'm just going to be left with a negative square root of 3. That is the tangent of 2 pi over 3. So, ladies and gentlemen, I just covered some main topics, main problems that you should be ready to explore on your semester 1 midterm exam in Precalculus. But we all know the problems that really are probably going to trick you up are going to be those word problems. So if you want to see the problems of me working through some common word problems that you can expect, then check out the next video I have for you here. And if you just want more examples and more practice for getting ready for that midterm, then go down and check out my description. I'll have tons of extra videos and resources made just for you. Cheers.